Hello everyone, my name is Filip Hanzely, and this is KAUST conference talk on our recent paper, Local SGD, Unified Theory, New Efficient Methods. So this is my joint work with Peter Richtarik and Eduard Grubner. So let me firstly introduce classical federated learning. So the goal of classical federated learning is something like that. What we want to do is we want to minimize average of n functions, where function f1 is owned by client 1, function fn is owned by client n, and so on, where this number of clients n is usually big. And you can imagine by n as number of mobile phones, for example, or something like that. So this is something large, and we have n of them, and each one owns function fi. So this function fi is constructed only from the data of ith client, and we have no control over the construction of this data, f1 up to fn. And ideally, we don't want this local data ever to be revealed. So we don't want to send the local data to the server, and we just want to minimize this sort of objective in some sort of like private fashion, ideally. And what is bottleneck of this training is communication. And this is what this work is about. It's more like how to, let's say, reduce communication or how to reduce the computation. Okay, so there is like the most natural baseline to train federated learning models, which is so-called local SGD or federated averaging in slightly more complicated form. So what local SGD is doing is that what we do is like we run several iterations of gradient descent locally to minimize just local function without communication. And then after the several iterations, we average it. Or alternatively, it can be written as follows, that x if k, which k is the current iterate, mod t isn't 0, then we run local gradient step on each machine. And if k mod t or k is divisible by capital T, then we average all x's, where x is the current local. And there are several variants of these methods in the literature, which fix some of the inherent problems with this method, for example. And also this method is analyzed in certain scenarios, depends on what we assume on the data. What we do in our paper, we propose some analysis framework for local SGD that covers all of it and also does something. In particular, in our paper, we propose analysis framework for local SGD, again, that covers all of it. So we allow for arbitrary local gradient estimator. So it doesn't have to be gradient, it can be stochastic gradient, it can be variance reduced stochastic gradient, for example, for better efficiency. We allow for arbitrary local shift. So the shift is important because local gradient as a local SGD is by default sort of non-stationary. So even if we are at the optimum, we can jump away. So this shift can correct for that. Then we analyze local SGD or allow for analysis under identical, similar, or heterogeneous data. And we allow for either random or fixed local loop. So random means like we have a random number of local steps in between of the iterations. And what is nice about our framework is that we give best known guarantees for all existing methods and recover best known rates from the literature, but we also give a lot of new and efficient methods. So if you want to learn more, please check out our paper or drop us an email. Yeah. Thanks for the attention.